Question?
I saw one on an old practice test. It was like it could be an acid-base reaction and an E1 or like a
Sure.
one of those.
Yeah. So I think I've seen for example, draw the product of that reaction. All right. Do you have a leaving group?
Yes.
Yep. Do you have a strong base or a good nucleophile? Yeah. So O-methyl minus, right? That's a localized negative on a singly bonded oxygen. That's going to be a strong base. That looks like sodium hydroxide.
Can you repeat what you just said there? How do you know it's a strong base? It's singly located.
You got a localized negative on an oxygen, right? So hydroxide, the oxygen's got one bond, localized negative on the oxygen. So any molecule that's got a localized negative on an oxygen is going to be a strong base. Methanol in this case is not going to be involved. If again, always the more reactive reagents are going to react. So if methanol is the only thing you have there, it's a weak base, weak nucleophile. It can react, but if you've got sodium methoxide in there with it, that's going to react first. Okay, so good leaving group on a primary carbon, you got a good base, strong nucleophile. You'd be sorely tempted, especially after 2.5 weeks of pounding you on chapter 7, to be like, that's an SN2 reaction. Totally, like, that would sort of be the reaction I would expect you to say, except, right, so this is strong base, good nucleophile. Okay, so it's a strong base. Kind of a strong acid over here. So again, proton transfer is usually the simplest thing. It's fast. It's as fast a reaction as you can have, because the atom that's moving is the smallest. And so what will happen here is instead of the SN2, you'll get that. All right. So the product you would wind up with, you need to draw at least this, and then I'm gonna. So now, does that make sense? Is that kind of what you were?
Yeah.
Yeah. So, generally speaking, if a Bronsted acid-base reaction that's thermodynamically favored can happen, it will. Okay. So the other thing then is, to figure out what the actual product of this reaction is, you'd have to know how much of the sodium methoxide you have. Okay, if I say we've got one equivalent, can stop there. Maybe. I'll come back and talk about that asterisk in a minute. But if we had two equivalents, then we've still got like one, for every molecule of the bromo acid, a methoxide is consumed. Right, so if we've got twice as much methoxide, then once we get to here, we still have one equivalent of methoxide that could do this, could do the SN2 on that bromo. Does that make sense? Right, so, no? Okay, good. You admit it when it doesn't. So, you've always got molar ratios, and these are always, this mechanism says one molecule of sodium methoxide reacts with one molecule of bromo acid. So if I've got half a mole of bromo acid and half a mole of sodium methoxide, they react, and at the end of that, I've got 0 of either of them, right? This reaction lies about 12 orders of magnitude to the right. So if I've got the same number of moles of methoxide as I do bromo acid, they react 1 to 1. I now have no more left. But if I've got half a mole of bromo acid and a mole of methoxide, so 2 molar equivalents, twice as many moles of methoxide as the bromo acid, all the bromo acid, the half a mole of bromo acid reacts with half a mole of the sodium methoxide. But then I've still got half a mole of sodium methoxide left.
So the negative charge on the oxygen wants the proton,
Yeah.
and then what happens to the proton?
Well, well, okay. Copy.
Because then the oxygen that's left there is just the OH that now doesn't have the AH.
Right, there you go. You also get methanol.
And then that negative OCH3 that's going to attack the leaving group is just another.
It's another.
So they're
Yeah.
separate. So there's an acid-base reaction because it's a strong base and another strong base.
Well, so you get the acid-base reaction is strong base and a strong acid.
Because hydroxide is a strong acid because it's an alcohol right there.
That's not a hydroxide, that's a carboxylic acid.
Okay.
Yeah. So if that was an alcohol, this wouldn't be as big of an issue, right? But that's a strong acid, carboxylic acid, strong base, so that they react. One molecule of methoxide reacts with one molecule of the acid.
So if you only have one molecule of the methoxide.
Right, so if you have a 1-to-1 ratio, you stop here. When you get this molecule, you don't have any more of that.
Yeah.
But if you had twice as much of that, right? Right, so if the concentration of the sodium methoxide is twice as much as the bromo acid, then once you get to here, you've still got, now you've got a 1-to-1 ratio of these two. And you could get that one to react with the bromo.
And then that's the SN2.
That would be the SN2. There's another complicating feature of this. And I can't remember if this would be, I think this is out there in a key somewhere, so I was wondering if it might be what you were asking. Let's say now, I'm gonna erase everything. Let's say so let's say that I've got a 1-to-1 ratio of methoxide to bromo acid. And so we make this. We get this as a product and, oh, sorry, it's not DMF. Sorry. So I'm just separating this out. We think the reaction's done, right? Methoxide reacts with the acid. We make a molecule of methanol. And we get this bromo carboxylate. Now, so just take this reaction. Forget what happened down here. You see this on your page. You have a leaving group. Yeah, you got a bromide still. You have a good nucleophile, strong base. you don't have a strong base. Take a look over at my, I don't know if anybody looked over there, I drew it, didn't draw attention to it. So the chart of good nucleophile, these are good nucleophiles that are not very strong bases. So sulfur, anion, or neutral, the anions are better. Phosphines, cyanide, azide, iodide, bromide, chloride, and carboxylates. Okay, so a delocalized O minus. So it's not very basic. It's the conjugate base of a carboxylic acid. Carboxylic acids are reasonably strong acids, so their conjugate bases aren't very basic. But they're still pretty good nucleophiles. So the answer to your question was, to my question was, yeah, you got a leaving group, and you got a good nucleophile. It's in the same molecule. Generally speaking, I don't want to put thoughts in your head, but generally speaking, students in Orgo 1 hate it when a molecule reacts with itself. I don't know why. I did too, but you get used to it. And in fact, this is a pretty fast reaction. So what this could do, probably would do, is that O minus will attack the bromide. Because remember, we draw that chain like it's a line, but all those bonds are rotating constantly. If you rotate right, this actually would, the way this reaction happens is you get bond rotation. So think back to the Orgo 1 stuff. And in one orientation, that nucleophilic atom is held basically right behind the carbon with the leaving group. And now this is a super fast, going to be a super fast reaction to kick that out. And your product would be that. Like I said, nobody likes it. It's an intramolecular SN2. So if you have a nucleophile and an electrophile in the same molecule, they'll react with each other. If they can physically come together, they'll react with each other. You look very unhappy. So the way to think about this is that a nucleophile? Is that an electrophile? Yeah. So, did you say yes?
Yeah.
Okay. So if they can come together, like if I did this, right? If you think this is okay, because now your mechanism there is going to be O minus hitting that. Then the only thing that's different about the reaction on the left from that red one is that I've tied these two together. So you should always be on the lookout for reactions where if any molecule has multiple functional groups and those can react with each other, they generally will. And so this would actually be a really hard one to predict. Like given the information I gave you here, where I didn't say anything about how much sodium methoxide you had, it's really hard. It would be, I say really hard, it would be impossible for you to tell me what the product will be. Okay? So you could, like I said, if you have a whole bunch of sodium methoxide, if I wanted to do this reaction here where I had methoxide clip off the bromide, I would use as much of that as I could. I would have like 20 equivalents of sodium methoxide. You're going to get the acid-base reaction to happen first, but then you want a lot of the nucleophiles left around. If I wanted this product, I would use just one equivalent of the methoxide. So I would pull this proton off, turn this group into a nucleophile, and my methoxide would go away and I wouldn't have it anymore. Right? I would consume all of that, and I'd be left with this. If I want that molecule, the carboxylate with the bromide, I'm probably out of luck. Right? Because you've got a good nucleophile, you've got a good SN2 substrate, and they're held together. Right? So it's going to be, there's nothing you can really do from the outside to make them not react with each Yeah, that took the whole thing. I've got a couple of minutes to take some questions. Any?
Just really quick,
Yeah.
are there Wiley Plus problems on the whole of Chapter 7? Because I think I checked like.
Yeah, there's like tons of them.
Okay, because I thought I checked a while ago and I saw only like SM2 stuff.
That's chapter 7.
Yeah, I know, but only SM2 stuff.
No, there should be. Anybody else got a?
It says only SM2, but it's like there's other stuff in there.
Huh,
If you
okay.
go to- If you go to like the read and learn section at the bottom.
I was gonna say, Wiley Plus has a lot more. Like, if I don't make it, I try to pick problems that I'm like, I would ask something like this. Like, I would hope you would know this.
Mm-hmm.
But Wiley Plus has terabytes of information that.
Okay. Because yeah.
Like, I try to pick those problems out because seriously, you guys could spend your entire, I don't know, your entire college existence just working Wiley Plus problems. I mean, it goes forever. And I don't want you guys. Again, there's no knowledge. Like, students are always like, I don't know. And I'm not trying to make this a moral judgment because I felt the same way. Like, you don't want to work on stuff that's not going to get asked, but you're going to. Right? I can't ask you everything you need to know about chemistry. So I'm going to try to pick a good sample. I'm going to try to be clear about what I'm going to ask. But like, if you go into Wiley Plus and you learn something that I don't ask, that's not a bad thing, right? Like, it might come in handy someday. But I would like to be clear with you on the sorts of things I will ask. And so the Wiley Plus problems I pick are sort of, I see the problem and I'm like, oh yeah, that looks good. Like, if I were forced into giving an online exam, I would choose this problem and let you work it. Sorry if it says only SN2, it shouldn't say that. It should be like all of it, yeah. I'll go check that. Any other last minute? So like I said, I'll be in the office this afternoon. If you have a question, email me. There's no game 7 tonight, so I'll probably pay more attention to my email. Ask me, I'll be around tomorrow. So tomorrow's Thursday, right?
Yes.
My other section is taking their exam tomorrow. So after that, like, I'll be totally at your disposal. All right. Yeah. Oh, right. You gotta.
But while we're leaving, go over really quick, what is integration in proton NMR cellular?
Integration tells you how many protons are making the signal.
Okay, so you can
So
get
like the signal for a methyl group will come in at 3.
right. And that's locally true, and you can also get the total amount of hydrogens from that as well, right?
Well, yeah, in principle, what it tells you is the relative strength. So like, you know, when you see an integration in an NMR, it doesn't, in a real NMR, it doesn't say, 3, it says,
2.96.
well, or it says 11.8. You have to go in and normalize it. So you sort of have to pick I have a good idea that this signal right here should be 2 hydrogens. But you really need to have some idea of what the molecule is.
Well, you're giving it.